So before we talk resonance, I'm going to talk about resonance in just a minute. I want to talk just about one more example of oxidation reduction. So we talked about single replacement. Okay. We're not going to talk about combustion because that's where the oxidation numbers get pretty crazy. So we're not going to flex on those, okay? But we can talk about combination and decomposition, right? So just a reminder, these guys are basically just opposites of each other, right? So if we have a combination reaction, we're starting with two products and going to, starting with two reactants and going to one product. Decomposition is just the opposite. So we're starting out with one reactant and going to two products. So let me give you an example. So I think last time we talked about this combination reaction. Right? So we have two reactants going to one product. So, is this balanced?
No.
Mm-mm. What do we need to do to balance it?
Add a 2 on the in front. Yeah.
2 in front of water, right? Which means that we have 2 times 2 is 4 hydrogens, and 2 times 1 is 2 oxygens, right? So now how do we balance the other side?
Put a 2 in front of the hydrogen.
Exactly. Right? So now in terms of a redox reaction, right? What are the oxidation numbers of this guy and this guy?
Oh, diatomic.
Will it still be zeros since it's an element?
That's exactly right. They're both elements, so they both have an oxidation number of 0, right? How do you know if something is diatomic as an element?
Why did I think that oxygen was gonna be... Oh, never mind. It even says most nonmetals are diatomic, which still means your oxygen number is 0.
Right. Not all of them, right? There are some nonmetals that are that aren't diatomic, right? But how do we know which ones are diatomic?
Oh, it's the cold beer thing, right?
Have no fear of ice cold beer. Yeah.
Oh, sorry.
Which makes me sad to think about right now because I can't have any.
Cold beer? Yeah.
Like, this is the worst time to not be able to drink.
Have a little.
I can't. I would be so sick. That's the thing. Like, people are always like, oh, you can have a little bit. I'm like, no, you don't understand. Like, my body hates everything. I don't want to put anything into my body. So, yesterday I was feeling really brave, and so I had pierogies for breakfast. It was such a bad choice, you guys. Oh, it was such a bad choice. I didn't know it until later on that day, but it was a very bad choice.
Oh,
yeah.
No.
So, okay. So let's talk about oxidation numbers on this side, right? So we aren't used to thinking about water as being ionic, but it kind of acts ionic. So in that case, what is the oxidation number for hydrogen here?
It's
Sorry. I know I'm making the most grossed out faces right now.
I still feel like it's 0.
Mm-mm.
It's not 0.
No, okay.
It's
Now,
+1.
it is +1, okay? But this is a really, really important point, okay? When they're elemental, it means that they're not hooked up with anybody else, right?
Oh.
So here, hydrogen, even though it's H2, is not by itself, right? It's in a compound with oxygen. Does that make sense?
Yeah.
So just because you see 2 of them doesn't mean that it's diatomic or that it's elemental, right? An element must be by itself, right? Meaning not hooked up with any other types of atom. Cool? So here, our oxidation state is +1, right?
Mm-hmm.
And
So
what
is
must...
it -2?
It is -2 here, right? So,
It's 'cause they're hooking up.
yeah, exactly. So
These
if you
stuff.
imagine that there's 2 H pluses, right? Right?
Mm-hmm.
Then there must be a total of +2 from these guys, right? And we know, what does oxygen like to make an anion wise?
Gain electrons? I can't think all of
No,
it.
no, that's okay, that's okay. So oxygen, right, in order to get to noble gas configuration, has to gain
Oh, it needs to be -3 or
-2, right?
That's what I meant.
So, right, for every 2 of these guys, you have 1 of these guys, right? Does that make sense? Kind of, sort of? Cool. Yeah, so this is why I think for a lot of people, chemistry is so difficult, because if you didn't understand something at the beginning of the semester, it will haunt you, right? So we use everything that we learned, we stack that information, right? So understanding electron configuration and how ions are formed is fundamental to being able to understand chemical reactivity, chemical behavior, all that kind of stuff, right? Cool. So now, whoops, just kidding. Sorry. Too far. Going from 0 to +1, what happened to hydrogen?
You lost some.
Lost electrons, which means it was
Oxidation.
oxidized, right? So what happened to oxygen here?
Gained some.
Mm-hmm. So if it gained electrons, it was reduced. Okay? So there's an acronym. I think acronym.
The oil rig.
Oil rig, yeah. So oxidation is loss of electrons, and reduction is gain of electrons. This is another one of those things that I write down every time I'm doing those. That and the number line. Okay. So this would be an example of a combination reaction, right? But if we just flipped the direction,
It would be breaking down.
yup,
Decomposition.
right? This would be a decomposition, right? Does that make sense, guys? So, in the decomposition, we're just flipping who's being oxidized and who's being reduced, right? Because now we have +1, -2, right? 0 and 0. So now we're going, hydrogen is going from +1 to 0, which is really where the number lines help, right? Because now we're not starting at 0, right? Here we started at 0, so it was pretty easy to see what direction we were going, right? But going from +1 to 0, we're gaining electrons, so we are reduced.
A reduction.
And for oxygen, going from -2 to 0, it lost electrons, so it was oxidized. Oops, oxidized. Does that make sense, guys?
Mm-hmm.
Cool. All right, so some question about resonance. Madison? You had a question about resonance? Sure, yeah. So Cl O3 minus, right? So this guy's name is, chlorate. It's a chlorate ion. It's one of our polyatomics. And we can draw the Lewis structure by starting off with our total valence electrons. So we have chlorine comes to the table with how many electrons? 7, yep. And oxygen comes to the table with 6 individually, and there are 3 of them, so yes, 18 total. And then the negative charge out here means that we need to add 1 extra electron, right? So we have 18 plus 8 gives us 26 electrons total.
Mm-hmm.
Cool. So now we put chlorine in the center, and we put the oxygens all around. And we've used 2, 4, 6 electrons in bonds. So we subtract that from our total, and we have 20 electrons left over. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So we used up all of our electrons. What's the next thing we want to check?
Formal charge.
Before we do formal charge, there's something else we need to check. The octet rule, exactly, right? So we have 2, 4, 6, 8 electrons around oxygen. 2, 4, 6, 8. 2, 4, 6, 8. 2, 4, 6, 8, right? So everybody has a full octet, right? Questions about that? We're okay with it. Okay. Okay, so then the next thing we want to check, Jessica, is the formal charge. Exactly, right? So this is where I like to draw in all of my little electron boys and section them off. So we've got oxygen came to the table with how many electrons?
18.
No, individually, 6,
Oh,
right?
Sorry.
So we had 6 electrons that oxygen came with, and directly around it here, it has 1, 2, 3, 4, 5, 6, 7, right?
Right.
So we subtract how many are around it to get a -1 charge, right? Since all of these oxygens have the same configuration, they will all have a -1 charge. Is everybody able to see that okay?
Yeah.
So now chlorine came to the table with how many electrons?
7.
Mm-hmm. And how many does it have around it here?
5.
5 electrons. So what's the charge on chlorine?
+2.
+2. So, is this charge minimized? Nuh-uh, right? So, we always know that negatives are going to be attracted to positives, right? So if we have extra electrons on these oxygens, they're going to be attracted to the positive charge on chlorine, right? So, because there's a +2 on chlorine, right, my initial thought is we need to make 2 double bonds to get rid of that +2 charge.
Okay.
Does that make sense?
Mhm.
So that's what I'm going to do down here. So, I did that pretty quickly. If you needed to take a little more time to do that, that's okay. Yes, Jessica.
It doesn't follow the octet rule anymore because it's 2, 4, 6, 8,
Right.
10 on
Yes.
chlorine.
Yes. So that would be the very next thing. Anytime we change a structure, we have to check the octet rule, right? So here we have 2, 4, 6, 8 around oxygen, 2, 4, 6, 8 around oxygen, 2, 4, 6, 8 around oxygen, 2, 4, 6, 8, 10, 12 around chlorine, right? But chlorine is one of the guys that can have an expanded octet, right? So row 2, no expanded octet, never, ever, ever, ever. But chlorine, being in row 3, can have an expanded octet, right? So an expanded octet allows you to have up to 12 total electrons around you, right? So this is good to go, right?
Oh.
Because chlorine can exceed the octet rule.
Gotcha.
Right? So, we have to check the formal charges again. Double check and make sure that our formal charges are good to go. So here, oxygen came to the table with 6 electrons, right? And we have 1, 2, 3, 4, 5, 6 electrons directly around it, right? So no formal charge there. Does that make sense, guys?
Mm-hmm.
Cool. Same with this oxygen, right? chlorine came to the table with 7 electrons, and it has 1, 2, 3, 4, 5, 6, 7 electrons here, right? No more formal charge on chlorine. You guys see now why I was motivated to put 2 double bonds in here? If I have a +2 charge here, then it means I'm going to need to share 2 pairs of electrons to get chlorine to not have that +2. And then last but not least, oxygen came to the table with 6, and it has 1, 2, 3, 4, 5, 6, 7 here, right? So it has a -1 charge on this oxygen. Everybody okay with how we got to this structure?
No question.
Yes.
Sorry. So if we were to draw a dipole, right, because it's not symmetric.
Okay, so this is kind of a weird instance. So when we're talking about polyatomic ions, we don't usually talk about dipoles because they have formal charges, right?
Okay.
So a dipole by definition is partial charges, right? In this case, we actually have formal charges.
Charge.
Right. So in terms of whether or not this molecule is going to be polar, it's so polar it's ionic, right?
Yeah.
Does that make sense?
Yeah.
Yes, whenever you change the structure, you have to reevaluate everything, not just formal charge, right? So you have to do the octet rule again. I think it's a good idea. We didn't do it here, but I think it's a good idea to just double check your electron totals, right? Because when you start moving electron pairs around, it's really easy to accidentally, add an extra pair in there somewhere. So usually there's going to be red flags when you do the formal charge, but it's never a bad idea to just double check your structure before you commit and say, does it still have 26 electrons, right? So here we have 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26 total electrons, right? So anytime we change a structure, we really should be evaluating all of those characteristics again. Is the octet rule satisfied? Is the number of electrons still correct? And then also the formal charge. Does that help, Madison? Cool. Okay, so now I think the next question in here is, why did I do the double bonds here and here, right? And the answer is, it's totally arbitrary. I just decided to do them there, okay? But there are equivalent structures that I can write where I have double bonds in different places, right? And that's called resonance. So if I take this structure and I say, I'm going to put these electrons back on this oxygen, and I'm going to make these into my double bonding electrons, right? Now I have a structure that looks like these, right? Where's my negative charge now?
On the other side.
So does this have a negative charge?
Mm-hmm.
No, right?
No, it's top.
It's this guy, right? Do you guys see that?
1, 2. Oh yeah, 7.
Mm-hmm. So now our negative charge is up there, right? Is there another structure that I could draw? Yeah. So I had double bonds here and here, right? Here and here. Now I want to have double bonds here and here, right? So I'm going to take this pair, put it back on that oxygen, and move the double bond over here. And I will end up with this as my structure, right? Now where is the negative charge?
It's on the left.
These guy, right? Do you guys kind of see what I mean about there being patterns to being able to see where formal charges are, right? Oxygen likes to have 2 lone pairs and double bond. It's kind of its thing, right? If it has a different arrangement than this, then it's probably going to have a charge unless it has 2 things bonded to it, right? So basically, oxygen likes to have 2 bonds and 2 lone pairs. That's kind of its deal. You don't need to know that. It's just something after you've done a lot of these, you kind of start to see, right? Are there any other resonance structures that we could draw? This is the hard part to see. So double check the resonance, which need to count the total electrons. So ideally, if you're being very careful, Madison, then changing the structure by just moving a pair of electrons shouldn't change it electronically, right? That's why it may sound kind of stupid that I do this arrows to move the electrons, right? But it really helps me know exactly what I'm doing with the electrons and where I'm putting them, so that I don't accidentally add in another pair, right? So since you guys are still relatively new to this process, I would recommend double checking everything every time you change a structure, right? So we did go through this kind of quickly, and that's fine, but I would say the better thing to do is always double check every structure that you do, right? Check for the formal charges, check for the octet rule. As you do more and more of these, you'll start to see patterns, and it'll be easier for you to see when you've done something weird, but for the time being, just check it all, right? Other questions?
On an example,
Sorry?
we have to draw all the resonance, or will it just say like is there resonance on the structure?
That's it. So the question of how many resonance structures there are, or could you draw them, is not something I'm going to ask you guys to do. What I want you guys to know is looking at this structure, right, that you can see that it has resonance, right? Now you can't look at this and automatically determine that that has resonance, right? You have to draw it out in order to know that. But I don't need you to be able to draw all of the different resonance structures. I just need you to be able to tell me that because this single bond is able to move around the molecule, right, there's going to be resonance, right? One of the other things that I want you to understand about resonance is it's really important in terms of minimizing the energy of this overall molecule, right? So one of the things we did up here was to minimize charge, right? We minimize charge because it minimizes the energy of the overall structure, right? You guys with me?
Mm-hmm.
Yeah.
Cool. So I think that there could be a question of why does this polyatomic ion form at all? If the negative charge is a hassle for the molecule, why does this guy like to have this negative charge, right? Does that make sense? Yeah? Well, the answer has a lot to do with this resonance, right? Because you don't have a negative charge on an individual atom, right? You basically have this one negative charge spread out over 3 atoms, right? That makes that negative charge super comfortable, right? Especially because oxygen loves to have extra electrons, right? Because it's so electronegative, this is basically just giving each one of these oxygens a little bit more electrons, right? Which makes it happy. Does that make sense? So this ability to move the negative charge from one oxygen to another is called electron delocalization or charge delocalization, and that is one of the things that leads to this molecular stability, right? Lowers the energy of the overall molecule. So this is why I think talking about polyatomic ions in nomenclature is kind of hard to explain why they occur until we get into the Lewis structures, right? So when you talk about the Lewis structures, I think it makes a little bit more sense why these things are able to form. Does that make sense, guys? Cool. Any other questions about Lewis structure-y type things?
This is like way back now.
That's okay.
Like, so sorry.
Yeah.
I was going over my one of the worksheets, like
Yes.
with the one with polarity and the intermolecular forces.
Yes.
And for some reason, I kept getting my structures would be right and drawn right, and I got it right if it was polar or non-polar. But for some reason, my electrons used in bonds and left over, like my numbers kept being different from yours.
So I think that depends on which structure you're talking about, the electrons in bonding, right? So like when I drew this first structure, right, my preliminary structure, I had 6 electrons in bonding, right? But how many do I have now?
10.
Right. Does that make sense?
So you count, I think I was counting my first structure, so always count.
Honestly, it doesn't matter. I'm not going to ask you to ever give me information about this preliminary structure, right? The only thing that I want to know about is what you got to in the end, right? Does that make sense?
Yeah.
Yeah.
That does.
Cool.
So I will, that makes perfect sense.
Yeah. And, you know, in terms of the kinds of questions that I might ask you on a quiz, I probably wouldn't even make you go from here and ask you how many bonded electrons there are, right? Because I think that's a little too much. I would probably give you this structure and then ask you how many bonding electrons there are. Does that make sense?
Yeah.
So yeah, so I don't want questions that are going to take 15 steps to answer, right?
Okay, and that's last week I said, oh, it takes me like 20 minutes.
Exactly. Right, and that's what we were talking about last week is, you know, each one of these structures takes a really long time to do. So I'm not going to ask you, every single question is not going to require you to draw a structure, right? In some cases, I'm going to give you a structure and say, you know, give me this characteristic of this structure, or which atom has a formal charge, or, you know, like any of these kinds of pieces of this puzzle, right? So the actual whole puzzle might be a question, right? But I mostly just want to know that you guys understand how each piece works, right? So that's how those are going to be tested.
Awesome. Thank you.
Yeah. So, Madison, in terms of similar to the quiz, I think that example that I just gave would be a good one, right? So I could ask you, given the chlorate structure, right, where is the formal charge on this atom, right? And then numbering each one of the oxygens and saying, is it 1, 2, 3, or maybe even 4 with the chlorine? Does that make sense? So that could be a possible question. How many bonding electrons are used in the chlorate structure? We said there's 10. So that question of how many bonding electrons are in the chlorate structure, I think is a really good type of question, because it requires you to, number one, know how to draw the structure or be able to see the structure, and also to know that chlorine is allowed to exceed the octet rule, right? Yeah. So that's kind of a twofer. Any other questions about Lewis stuff? All right.